Hi everybody, today we're going to learn about heats of formation or enthalpies of formation. So this is another way to calculate the delta H for a reaction. Heats of formation, their symbol are, you see delta H, but then with a little degree sign that means standard, at standard conditions, like room temperature, 1 atm pressure, and there's a little F there that stands for formation. So what is heat of formation or enthalpy of formation? It is the enthalpy change or the heat that is transferred when you form 1 mole of a substance from the most stable forms of its component elements at standard conditions, which are 298 Kelvin and 1 atmosphere. So what does that mean again? So if I were to form 1 mole of my compound from its elements, that is the heat of formation. So take a look at this table here that lists a bunch of heats of formation. Let's look at carbon dioxide. So carbon dioxide is right here. CO2 is negative 393.5 kilojoules per mole. So what does that mean? It means if you were to form 1 mole of carbon dioxide from its elements in their natural state, that's the heat that's transferred. So if I were to take carbon dioxide and form 1 mole of it, well, what elements make that up? Well, carbon in its natural state is solid, and oxygen in its natural state is diatomic gas. So if I take a carbon plus O2, that would yield CO2. The delta H for this formation reaction is that number right here, which is negative 393.5. Let's look at water. Water has 2 values here. There's water and there's water vapor. So if I take 1 mole of my water and form it from its elements in their natural state, that would be the delta H for that reaction. Now notice, normally when we write, if you were to form water, right, H2O, it's made up of hydrogens and oxygens, which are both diatomic. To balance it, you would do 2, 1, 2. That would not be the correct equation for the formation of water, right? Because by definition, it's forming 1 mole of your compound. So this right here coefficient has to be 1. So if you need to do this to balance it, but then you have to reduce to make that 1, then that would be 1 H2 and half O2. That's why it's written this way, because it's forming 1 mole. If I were to double it like this, then the delta H would be double what that number is telling us in the table. Now notice that there's a difference in liquid versus gas. That's because the liquid and the gas have different potential energies, right? So if you actually subtract those two, you'll see that that's the heat of vaporization or the heat of condensation of water. Because if you subtract those 2 equations from each other, you're going to get H2O liquid going to gas or gas going to liquid. And so it's going to be the heat of vaporization or the heat of condensation. That's pretty cool. So how do you use heats of formation to calculate delta H for the reaction? So delta of anything, the change in anything, is final minus initial. So if we are looking at a chemical reaction, the initial is the reactants and the final is the products. So we could use heats of formation by looking at an equation and saying we're going to add up the heats of formation of the products minus the heats of formation of the reactants, and that's going to give you delta H for the reaction. So final minus initial products minus reactants. And on the test, you will be given this table right here so that you can refer to it. In the question, it will say, using heats of formation, calculate delta H for this reaction. So let's try a couple of examples. Example 1, it says, calculate the heat of reaction for the reaction between ammonia and oxygen to form nitrogen and liquid water. So first thing you want to do is write out your equation. So we are reacting ammonia and oxygen. So ammonia is NH3. And we're going to add oxygen to it to form nitrogen and liquid water. Let's balance it. So you would need 4 of those, 2 of these to balance out our nitrogens, 6 waters, and 3 O2s. Okay, so then you're going to say delta H of the reaction, since we're using heats of formation, is going to be the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Okay, so products minus reactants. We're going to start with the products. These are my products. So I have 2 moles of N2 first. 2 moles of N2. I look at my table and try to find the value for it. You'll see N2 is not listed. How come? Well, because if the standard heat of formation is how much heat is transferred when you form 1 mole of your compound from its elements, well, if it's an element in its natural state, then its heat of formation is 0. So that's what this is saying right here. The standard heat of formation of the most stable form of any element is going to be 0, meaning that, nitrogen is a diatomic element, so N2 gas is going to be 0. I2 solid will be 0. Carbon solid would be 0. So whatever the most stable form of your element is, its heat of formation is going to be 0. So nitrogen just has a heat of formation of 0. 0 kilojoules per mole. Now, you'll ask me, well, if it's 0, why do I need to put it into my work? That's just how you show your work. If you don't write it, that's fine, but if your final answer is wrong, then you won't get partial credit for your work. So make sure that you put it into your work. That way I can follow, where you made your mistake. Okay, next I have 6 moles of water. It's liquid water. So you go to your table, look up the value, and it's negative 285.8 kilojoules per mole. Okay, these are my products. So all of this minus, and then we're going to do our reactants. So our reactants, we have 4 moles of ammonia. And the value on the table for ammonia is negative 46.19 kilojoules per mole. Then we have 3 moles of O2. And remember, 0 kilojoules per mole. And you just add them all up together. You get negative 1530 kilojoules. And that's our answer. Let's try another one. Calculate the heat of reaction for the combustion of 1 mole of propane, which is C3H8. So let's first write out our equation. C3H8. We're combusting it, so we're going to add O2. We're going to form CO2 and H2O. And we're going to say it's gas here because if it's combustion, it's going to be probably pretty hot. Let's balance it. So we need 3 of these, 4 of these, and 5 O2s. So if we're using heats of formation, we're going to say delta H of the reaction is equal to the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. So we'll start with the products. We have 3 moles of CO2. The value for CO2 is negative 393.5 kilojoules per mole. Plus, then we have 4 moles of water. We're going to say it's water vapor this time. So the value for that one is negative 241.8 kilojoules per mole. Getting those values just from the table. Minus my reactants. I have 1 mole of propane. The value for that one is negative 103.85 kilojoules per mole. And then finally I have 5 moles of O2. Value for that is 0 kilojoules per mole because it's an element in its natural state. Add all these up together and you end up with negative 2,950, or sorry, wrong answer, negative 2,044 kilojoules per mole. That's our answer. Last problem here. It says, how much heat is released when 63.5 grams of propane is burned? So, first we're going to write out our equation. Well, we just calculated that, right? We just burned propane in the previous example. And we already got that delta H of the reaction is negative 2,044 kilojoules. So how is this one different from the last problem? Well, We calculated this from the table. So this is for the reaction as written. This is for how much propane? Well, it's for 1 mole of propane. The question is asking me for 63.5 grams of propane. So if this was the question on the test and it says using heats of formation, calculate this, you would do all what we just did in question 2, and then you would do one more step. So this is stoichiometry, right? This is putting heats of formation and then stoichiometry. So what we just calculated from the table is for 1 mole of propane. Now we want it for 63.5 grams of propane. Do you remember how to do that? So you would say I have 63.5 grams of C3H8. Change that to moles. Grams on the bottom, moles on top. 1 mole of propane is 44.0 grams of propane. And then we put moles here because that's not what we want. We're looking for kilojoules, right? We're looking for how much heat. So I can relate it by saying it's negative 2,044 kilojoules for every 1 mole of propane. And this gives me negative 2,950 kilojoules.